On September 22 in 1969, in Murchison, Australia, a meteorite streaked across the sky, fragmenting before impact. When scientists analyzed its carbonaceous chondrite fragments, they found something extraordinary within: over 90 different amino acids, the very building blocks of proteins. This wasn't contamination. These molecules were extraterrestrial, a profound clue from the cosmos. It opened up a universe of possibilities about life's origins. The vast emptiness between stars, known as the interstellar medium, is surprisingly not empty at all. It's a swirling cosmic soup of gas, mostly hydrogen and helium, punctuated by tiny dust grains. These microscopic particles, often no larger than a smoke particle, are the critical catalysts where complex chemistry begins. They are the initial workshops of creation in our galaxy. Cosmic dust grains are not just inert specks, they are complex structures made of silicates, carbon, and metallic elements. Crucially, in the frigid depths of space, these grains acquire icy mantles of water, carbon monoxide, and methanol. These frozen surfaces act as tiny reaction chambers, shielding molecules from harsh radiation and allowing them to meet and combine. Here, simple atoms can evolve into astonishingly complex molecules. Prebiotic chemistry describes the chemical processes that could have produced life's complex molecules from simpler, inorganic precursors, all without the presence of living organisms. Scientists are now discovering that this intricate chemistry isn't confined to early Earth. Instead, the universe itself seems to be a vast laboratory, constantly churning out organic compounds. This suggests life's fundamental components are a cosmic inevitability. Amino acids, the fundamental units that link together to form proteins, are among the most exciting discoveries in interstellar space. Through radio astronomy, scientists have identified glycine, the simplest amino acid, in regions like the Sagittarius B2 molecular cloud. This detection confirmed that these essential building blocks for protein synthesis can form naturally in deep space. You are literally seeing the universe write its own code. Beyond amino acids, astonishing discoveries include the detection of nucleobases, crucial components of DNA and RNA. Adenine, guanine, cytosine, and thymine, the letters of our genetic code, have been found in carbonaceous chondrite meteorites. This means the very blueprints for hereditary information might have been delivered to early Earth from space. The universe centers the alphabet for life. Scientists use sophisticated laboratory simulations to recreate the extreme conditions of interstellar space, including vacuum, cryogenic temperatures, and intense radiation. By exposing simple ices like water and methanol to UV light, they have successfully formed complex organic molecules, including amino acids and sugars. These experiments prove that the cosmic dust grains really can be the nurseries for life's precursors. It's chemistry on a cosmic scale. Protoplanetary disks, the swirling nurseries where new stars and planets are born, are rich reservoirs of these complex organic molecules. These disks inherit much of their material from the parent molecular cloud, including the preformed organic compounds on dust grains. As planets coalesce within these disks, these life-enabling molecules are directly incorporated into their primordial soup. Your very origins might have come from this cosmic dust. The combination of abundant water ice and pervasive ultraviolet UV radiation in space acts as a powerful catalyst for forming complex molecules. UV photons break simple molecular bonds in the ice mantles, creating highly reactive free radicals. These radicals then recombine into larger, more complex organic structures like polycyclic aromatic hydrocarbons (PAHs). It's a natural process transforming basic elements into intricate chemicals. The Murchison meteorite, which fell in Australia in 1969, remains a cornerstone of astrobiology due to its extraordinary composition. It contained more than 90 distinct amino acids, many not found on Earth, unequivocally proving their extraterrestrial origin. This single-space rock provided tangible evidence that complex organic molecules form readily in the cosmos. It was a message from beyond, delivered to our doorstep. Comets and asteroids are not merely cosmic debris. They are ancient time capsules preserving interstellar organic molecules. These icy and rocky bodies served as crucial delivery vehicles, raining down on early Earth and seeding our planet with a diverse array of these compounds. They might have provided the necessary ingredients for life to first emerge here. Without them, our planet could be barren. The RNA world hypothesis proposes that RNA, not DNA or proteins, was the primary genetic material for early life, capable of both storing information and catalyzing reactions. Remarkably, some of the most complex organic molecules found in space, such as ribose, a sugar in RNA, and nucleobases, directly support this hypothesis. This discovery suggests the raw ingredients for an RNA world were widely available. Could the universe be an RNA factory? Glycoaldehyde, the simplest sugar, has been famously detected in the vast star-forming region Sagittarius B2, a hot core near the galactic center. This discovery is pivotal because glycoaldehyde is a key precursor to ribose, the cushion sugar component of RNA. Its presence confirms that essential sugars, not just amino acids, are forming naturally on interstellar dust. You are looking at chemistry's first sweet steps towards life. Beyond UV radiation, cosmic rays, high-energy particles traveling through space also play a vital role in interstellar chemistry. These rays can penetrate deep into molecular clouds, initiating chemical reactions by breaking molecular bonds and creating reactive fragments. This constant bombardment helps sustain the complex chemical synthesis occurring on dust-grained surfaces. It's a constant cosmic energy infusion powering molecular evolution. The panspermia hypothesis posits that life, or its precursors, could be distributed throughout the universe via comets, asteroids, or even microbial spores. The widespread detection of complex organic molecules in interstellar dust and meteorites lends significant credibility to this idea. It suggests that life's ingredients are not only ubiquitous but also readily transportable across vast cosmic distances. Could life be an infection passed from star to star? Formaldehyde, a simple organic molecule, is one of the most abundant organic compounds detected in the interstellar medium. It serves as a crucial building block for much larger, more complex molecules, including sugars and potentially even some amino acids. Its widespread presence highlights how readily basic organic chemistry occurs across the cosmos. This common molecule is the universe psalter for life's chemistry. While glycoaldehyde, a precursor to ribose, has been found, the detected detection of ribose itself in interstellar space remains an elusive but highly sought-after prize. Finding extraterrestrial ribose would provide definitive evidence that all the essential building blocks for RNA, including its sugar backbone, can form in space. Such a discovery would dramatically strengthen the case for an RNA world beginning of Earth. The universe may hold this missing piece. Infrared astronomy is an indispensable tool for identifying complex molecules hidden within dense interstellar clouds. Dust grains obscure visible light, but infrared radiation can penetrate these veils, revealing the unique spectral fingerprints of organic compounds. Telescopes like the James Webb Space Telescope are revolutionizing our ability to map and understand this intricate interstellar chemistry. We are finally seeing what was once completely hidden. The habitable zone around a star is traditionally defined by the presence of liquid water, crucial for life as we know it. However, the discovery of complex organics forming far outside these zones completely changes the picture. These molecules don't need to originate in the habitable zone. They can be delivered there by comets and asteroids, greatly expanding the potential for life. The universe might be far more alive than we think. Kuiper belt objects, icy bodies orbiting beyond Neptune, are pristine remnants from the early days of our solar system. These distant objects act as deep freeze storage units, preserving the primordial organic molecules incorporated from the interstellar medium. Studying their composition, perhaps through future missions, could reveal an untouched record of life's fundamental ingredients. They are cosmic time capsules waiting to be opened. Saturn's moon Titan presents a unique natural laboratory for studying complex organic chemistry with its dense nitrogen atmosphere and methane lakes. Despite lacking liquid water, intense solar radiation drives the formation of vast arrays of organic aerosols, forming haze layers high above its surface. This showcases how diverse planetary environments can foster the genesis of prebiotic molecules. Life might find ways beyond our expectations. As we discover thousands of exoplanets, the search for life extends to their atmospheres, seeking biosignatures, chemical indicators of life. The understanding that interstellar dust already seeds protoplanetary disks with life's building blocks fundamentally impacts this search. It means many exoplanets might start their lives already preloaded with complex organic material. You are looking at a universe primed for life's emergence. The field of astrobiology is rapidly advancing, with new telescopes and missions constantly pushing the boundaries of our knowledge. Future probes to comets and asteroids, alongside more sensitive space telescopes, promise even more astounding discoveries regarding interstellar organics. We are on the verge of unlocking the deepest secrets about our own origins and the prevalence of life in the universe. What else is hidden in the dust? The accumulated evidence strongly suggests that the universe possesses a universal recipe for generating life's fundamental building blocks. From frigid molecular clouds to meteorites, the spontaneous formation of amino acids, nucleobases, and sugars appears to be a common cosmic process. This universal chemical pathway implies that life might not be a rare accident, but rather a widely distributed phenomenon. You might not be as alone as you think. The journey from cosmic dust to complex life is one of the most profound stories the universe has to tell. If you are captivated by these glimpses into life's origins, make sure to like this video and subscribe to our channel. What do you think is the most surprising discovery about interstellar dust? Share your thoughts in the comments below, and let's continue to unravel the universe's greatest mysteries together.